If we want to compare this to what we were looking at in 7A with the conservation of energy, in 7A, we were looking at a system that has maybe several different types of energy, but as time passes, the total energy doesn't change. Total energy of a closed system doesn't change as time passes. In other words, delta E total equals 0. Or alternatively, how would we modify that for an open system? If it's an open system, instead of saying delta E total equals 0, how would we write that differently if it's an open system? What could cause changes to the total energy? Yeah, we could have heat and work. The kinetic energy and potential energy could certainly be types of the total energy, types of energy involved. So maybe we might split this delta E total into delta kinetic energy plus delta potential energy. But those are types of energy. What actually causes the change to energy is these transfers. Heat being transferred to or from the system and work being transferred to or from the system. So the heat and work are the processes that cause that change in whatever types of energy are changing. So in 7A, that's the main idea of energy conservation. I mean, not just in 7A, but in general, this is the main idea of energy conservation. That as time passes from one instant in time to a later instant in time, the total energy does not change if it's a closed system. Or if it's an open system, the total energy can change, but the amount of change is equal to the heat and work combined. Any questions on that review so far? So the 7B extension of this same idea is the idea of energy density conservation. And this grows out of the concept that instead of looking at a nice compact system like, I don't know, maybe you're putting a 1 kilogram block of hot iron into 10 kilograms of cold water or something like that. In the systems we're going to be looking into, it's not as straightforward as just this is one object, we put them together. We're going to be dealing with a much more complicated looking system, such as looking at fluid flowing through pipes, looking at a pump pushing water uphill, or looking at comparing the pressure at different depths in a tank of water. So it's not just one unified object, it's this continuum of fluid. So instead of looking at the total energy of the whole system, which is usually not going to be useful information in these contexts, we want to look at how concentrated the energy is at each location. Maybe at this location, there's a certain amount of energy per cubic centimeter or per cubic meter, or however you want to measure it. And over here, maybe we've got a different amount of energy per cubic meter. So we're not going to be looking at how much energy there is total. We're going to be looking at how tightly packed the energy is. Energy density, we're defining as energy over volume. The amount of energy per volume, the amount of joules per cubic meter. And that's going to be the units, by the way, joules per cubic meter. And the idea of conservation of energy density is very similar to the idea of conservation of energy, but we're not really looking at it in terms of time. We're not comparing the energy at one time to the energy at a later time. Instead, we're comparing positions. If we're comparing one position in, let's say, a pipe or something, and then another position in the same pipe, the same fluid system, we would assume that the total energy density doesn't change. And this is actually very similar to another idea we did see in 7A. Where else in 7A do you remember seeing something about how tightly energy is concentrated, and the idea that the energy concentration at this location and the energy concentration at this location should be the same? The idea that energy is evenly distributed. Where have you seen that before? Yeah, the idea of modes, the equipartition theorem of modes, that if you're looking, yeah, the 1/2 kBT, that each molecule, each mode in each molecule should have the same amount of energy on average, assuming that the thermal energy or the temperature is uniform throughout. The idea that energy should be evenly distributed to all the modes in the molecules is a very similar concept to this. Here, instead of looking at per mode, though, we're looking at it in terms of volume, the amount of energy per cubic meter. We're assuming that the energy is evenly spread out through space within that one fluid system. So instead of looking at energy changing as time passes, we're looking at energy density comparing one location to another location in space. So we'd say the total energy density doesn't change from location to location. In the same closed fluid system. Closed, as usual, means there's no heat or work entering or leaving. Same fluid system is kind of a trickier concept, I think. The idea of the two locations being in the same fluid system, one way to look at that is that you can draw a path from one location to the other without leaving the fluid. For example, if you just got, let's say, some jar full of water, and let's say over here you've got another jar full of water. And let's say we label some points. Let's say this is point 1, this is point 2, and this over here is point 3. If you're comparing point 1 and point 2, you can draw a path from point 1 to point 2 that doesn't leave that fluid. That entire path goes through just water. So we'd say points 1 and 2 are part of the same fluid system. Point 3, though, if you try to draw a path from 1 to 3, you have to leave the fluid. You have to go from water to air and then back to water again. So we would say points 1 and 3 are not part of the same fluid system. Any questions on that so far? And one of the tricky aspects of this, one of the tricky aspects of this is that motion actually matters here. If you've got, even if it's the same fluid, let's say you've got water that's moving and water that's not moving, those count as separate fluid systems, even though it's the same substance. And a typical example you're going to see of this is if you've got a pipe with water flowing through it. And if you've got what's called a standpipe on top of that, basically just a vertical section of pipe sticking out the top, usually with the top end open. And you are in a situation like this, you're going to end up with some of the water supported in the pipe here. And this water here is going to be stationary. It might start to flow up at first, but at some point you're going to reach a level where the water just stays where it is. And if you want to compare some points, let's say you want to compare a location in the fluid, let's call this point 1, the moving water, and let's say this location on top of the stationary water. Would you consider those to be part of the same fluid system? Not in this case, because if you try to draw a path from 1 to 2, you're actually passing through two separate fluids or two separate fluid systems. You've got the stationary water and the moving water and the stationary water. So in a situation like that, usually what you want to do is introduce a new location. Let's call this point at the border point 3. If you're going from 1 to 3, that path is entirely in moving water. So 1 and 3 can be considered part of the same fluid system. If you go from 3 to 2, you're going only through stationary water. So 3 and 2 can be considered part of the same fluid system, which means you can run a Bernoulli equation analysis on the 1 to 3 change and separately run a Bernoulli equation analysis on the 3 to 2 change. So you can indirectly link points 1 and 2 together by comparing them both to this in-between point 3. And this is often a very useful approach. Anytime you're comparing two locations that aren't part of the same fluid system, it's useful to put in extra labeled locations at border zones. Anytime you've got an interface, a surface where two fluid systems come together, just mark and label a new location at that border between them. And then you can compare a point in the fluid, in one fluid system, to the point on the edge, and the point on the edge to the point in the other fluid system. So interfaces, the surface where two fluid systems meet, are very useful locations to compare here. Likewise, point 2 is going to be very useful because it's the interface between the stationary water and the air. So that's a very useful way to compare those fluids. Any questions on that so far? So let's try writing this out as an equation. Instead of writing delta E total equals 0 as time passes, we're going to write delta energy density total equals 0 from location to location. So for a closed system, we've got delta E total over volume. That is the change in total energy density equals 0. And we got to be careful about these deltas here, because usually for time passing, delta means what? What is delta, or how is delta usually written out? Yeah. Delta is typically written as final minus initial. In other words, the value at the later time minus the value at the earlier time. In this context, though, we're not talking about time at all. We're assuming that everything's being measured at the same time, or perhaps more accurately, we're assuming that time doesn't matter. We're assuming we're dealing with what's called a steady state system. That is, it's not changing as time passes. So instead of thinking of the deltas as final value at some later time minus initial value at some earlier time, it's probably best to think of this as just the value at one location minus the value at the other location. So the energy per volume at location 1, or let's say location 2, minus the energy per volume at location 1. So we're not subtracting value at one time minus value at another time. We're subtracting value at one location minus value at another location. And since we're not really dealing with time passing here, the order doesn't matter. We could subtract the value at location 1 minus the value at location 2 instead. The important thing is to be consistent about it. So if you're going to be subtracting value 2 minus value 1 for one thing in the problem, you need to be also subtracting value 2 minus value 1 for everything else in the problem. So you want to choose an order of subtraction and be consistent about it. But that's the interpretation of delta here. It's not the change as time passes, it's the difference from location to location. Because we don't care about passage of time here. We're assuming we're talking about a system that doesn't change significantly as time passes. Stuff is moving, but it's moving in a consistent way. You take a measurement of how fast the fluid is flowing, you come back 5 minutes later, take another measurement, and you get the same result. We're assuming that this does not change significantly as time passes. If there are any changes that could happen, we're assuming they've already finished happening and they've settled into a steady state equilibrium. Any questions on that so far? So let's expand this idea of change in energy density. In a fluid system like this, what types of energy could be changing if you're comparing location to location? Yeah, maybe there's a difference in speed. Maybe the fluid in one location and the fluid at another location are traveling at different speeds. So we could have kinetic energy, although we're going to call this kinetic energy density by dividing it by volume. And yeah, height's going to matter. So we're going to have a potential energy density, a potential energy of gravity density. And I guess I should put deltas here also. And there could also be thermal energy, but we're generally going to treat that as heat gain or loss. We don't really care what temperature the fluid is. If the fluid is gaining or losing, raising or lowering its temperature, we're just going to treat that as gaining or losing heat. So we'll put that on the other side of the equation if we're dealing with an open system. But let's assume it's a closed system for now. If we fill in the usual formulas there, what's our usual formula for kinetic energy from 7a? Yeah, 1/2 mv squared. Or since we really care about the change, I'll write that as 1/2 m delta speed squared. And again, that delta is from location to location, not from time to time. And then we're going to divide that by volume. And what about our usual formula for a change in potential energy of gravity? Yeah, mg delta y, including that delta because we are talking about a change. And again, that delta is talking about the difference from location to location, not time to time. So we're not really talking about like water falling. Even if the water's all staying still, maybe we're comparing the height at this location in the water to the height at this location in the water, or whatever fluid it happens to be. And a very convenient shortcut here, if you're talking about mass divided by volume, and we've got a mass divided by volume here as well, what's that the definition of? What do we call mass over volume? Yeah, this is the density, the mass density of the substance, how concentrated the mass is, how much kilograms per cubic meter. So we can replace mass over volume with just density, usually written as the Greek letter rho. Looks kind of like a curvy letter P. That is the Greek letter rho. So we get 1/2 times density of the fluid times change in squared speed, plus density of the fluid again, times acceleration of gravity, the usual 9.8 meters per second squared, times the change in height. So these are our new formulas for change in energy density, change in kinetic energy density, change in potential energy density. And energy density you'll sometimes see referred to as head. And I think this is from fluid flow engineering, like dealing with pipes and stuff. Head represents, if you take a standpipe, like I was drawing earlier, and measure how high the water rises in that standpipe, we refer to that height as the head that the water reaches. So this would be sometimes called the kinetic head and the gravitational head. But that's just another word for energy density. So we can fill those in as our change in kinetic energy density and our change in potential energy density as actual formulas. We've got our 1/2 rho delta speed squared and our rho g delta y. And one of the really convenient things about this, if we were looking at this in terms of mass and in terms of volume separately, we'd have to know things like what's the total mass of all the fluid in this system? What's the total volume of all the fluid in this system? And that's usually very inconvenient to deal with. But by simplifying that to density, this is just the density of the fluid. If this is a known fluid, you don't really even need to measure that. You can just look it up. You can look up the density of water, the density of oil, the density of mercury, the density of air, whatever fluid you're dealing with. If it is a known standard fluid, you can just look up its density on a data table. And probably the most common one you're going to be seeing is water. And water actually has a very standardized density because the metric system is based on water. Specifically, the metric system defines 1 gram, or originally defined 1 gram, as the mass of exactly 1 cubic centimeter of water. So 1 cubic centimeter of water has a mass of exactly 1 gram by definition. If you run the unit conversions on kilo versus centig cubed, you end up with 1,000 kilograms per cubic meter. So that's the density of water. Good thing to have memorized just because it's a very, very straightforward, convenient number to work with. And it shows up all the time because we often deal with water. Any questions on that so far? And while we're at it, let's take another look at, or closer look at the units of measurement for energy density here. All this energy density stuff, energy over volume. What are the units of measurement we use for that? What's energy measured in? What's volume measured in? What are the usual units of measurement for energy? Yeah, energy is measured in joules. Volume is measured in cubic meters. So energy density can be measured in joules over cubic meters. There are some interesting ways we could split that up though. If you split out joules, specifically if you take a look at joules in the terms of the definition of work. Anyone remember how we defined work in the first place back in 7A? What is work? That is, if you want to count as doing work to an object, what do you have to be doing to an object to count as work? Yeah, you've got to be applying a force, and there's got to be displacement. There's got to be motion. Force times displacement. The amount of force being applied to the object multiplied by how far the object travels. And if we fill in the units there, work is a transfer of energy, so that better be measured in joules. Anyone remember what force is measured in? Yeah, force is measured in newtons. And distance, of course, is going to be measured in meters, yeah. So this is a very convenient substitution you can make. Anytime you see joules, you can, if you want, replace it with newtons times meters. And anytime you got newtons times meters, you can replace it with joules. If we make that substitution here, if we replace joules with Newton meters and divide by meters cubed, what do you get if you simplify that? Yeah, one of the meters cancels out. So you're left with just newtons over meters squared. And newtons is a force. Meters squared is measuring what? What's that a unit of measurement for? If you describe something as, yeah, this is area, right? Meters times meters, that's a distance times a distance, so you get an area. So that means that force over area is at least the same units of measurement as energy over volume. And it turns out that that means that these are very closely related concepts. Anyone know what force over area is called? If you're talking about how much force you have divided by how much area is spread out over. Like for instance, if I'm just pushing on the whiteboard here with my hand, The force I'm applying is spread out over the area of my handprint. How would we describe how much that's spread out? Yeah, this is pressure. The distribution here, the amount of force per unit of area, is called pressure. And we talked about pressure a little bit in 7A in terms of the ideal gas equation and pressure versus volume graphs. But this is what pressure actually means. Pressure is defined as how spread out or how concentrated the force is. The amount of force being applied on some surface divided by the area of that surface. This is very relevant for fluids because you've got, for instance, in a pipe, you've got the water pushing out on all the walls. So that push divided by the surface area of those walls is the pressure. And that means that pressure, even though pressure doesn't really look like an energy density, we're not defining it as an energy over a volume, but it turns out to have the same units of measurement. Newtons per square meter is exactly the same as joules per cubic meter. And we also call this pascals. So pascals is the official unit of measurement for pressure in the metric system. And 1 Pascal is the same as 1 Newton per square meter by definition, which also is the same as joules per cubic meter. And because pressure counts as pressure has the same units as energy density, we can fill in pressure as a form of energy density in this equation. So pressure acts as a form of energy density here. Change in pressure plus change in kinetic energy density plus change in gravitational potential energy density adds up to 0. These are the 3 forms of energy density we're going to be talking about. And they all have the same units of measurement. These are just 3 different ways of writing the same units. In fact, you can even simplify this further. If you fill in the fact that newtons equals kilograms times meters per second squared, or alternatively, if you fill in joules as kilograms times meters squared over second squared, fill that in either of these and simplify further. For instance, replace newtons with kilogram meters over second squared. One of the meters cancels out, you get kilograms over meters times seconds. So this is just another way of writing the same thing. Joules over cubic meters, newtons over square meters, pascals, kilograms over meters times, I guess that's meters times seconds squared. But these are just 4 different ways of writing the same units of measurement. These are all equally valid ways of writing the units for any of these terms. And which one you want to use really depends on the circumstances. Joules per cubic meter heavily emphasizes this as an energy density. Pascals or newtons per square meter emphasizes this as a pressure. Kilograms over meters times second squared looks kind of meaningless on its own right, but it can be useful if you ultimately just want to be simplifying all the units anyway. You may as well start here, and then you've got everything reduced to the most basic units. But they're all exactly the same, just different ways of writing it. Any questions on that so far? All right, so this is the Bernoulli equation for a closed system, if there's no heat or work entering or leaving the system. And I think we can get some conceptual applications out of this right away before we even add any more detail here. If you're comparing 2 locations in, let's say you just got a tank of water. And let's say it is some number of meters deep, let's say 5 meters deep. And you want to find the pressure at the bottom. If you want to find the pressure at the bottom, what's another location we could compare that to? Because the Bernoulli equation is all about comparisons with these deltas. So what's another good location to compare that to? Is there any location in this entire tank of water where we would know the pressure or where we might be able to find the pressure? At the top, yeah. And the top is very useful because the top is an interface between two fluid systems again. We've got an interface between the water and the air. And one of the important properties of any interface between two fluid systems is that at that point, both fluid systems have to have the same pressure. The air pressure at this location and the water pressure at this location have to be the same pressure. If they were different pressures, like let's say the air was higher pressure than the water would be pushing the water in, or if the water was higher pressure, it would be pushing the air out. So it would still be in motion. It wouldn't be a static equilibrium. So if everything's settled down to its steady state, we have to assume that at this point, the air pressure and water pressure are the same. So if we know the air pressure, which should just be 1 atmosphere, then we know the water pressure at this point also. So let me label these, let's say 0.1 and 0.2. So at this point, pressure P1 is atmospheric pressure. And points 1 and 2 are in the same fluid system because a path from 1 to 2 goes only through the water. It goes only through one fluid system, stationary water. So if we're comparing point 1 to point 2, as you go from point 1 to point 2, comparing it to the Bernoulli equation, what's the most obvious thing that's changing from point 1 to point 2? Yeah, the height. Y is changing, specifically as you go from 1 to 2, being consistent about our direction here. From 1 to 2, what's happening to the height? Right, height is decreasing. So going back to our Bernoulli equation, we can say that delta Y is a negative value from 1 to 2. And if this is a negative value, there's got to be some positive also to make sure they add up to 0. So one or the other of these, or at least both of them combined, has to be a positive value. What about speed? What's the speed of the fluid at point 1 and what's the speed of the fluid at point 2? Is this fluid moving? Yeah, there's no change. This fluid is not moving. It's what we would call a hydrostatic system. Hydro meaning water, static meaning stationary, not moving. In a hydrostatic system, there's no motion. So the speed 1 is 0, and speed 2 is also 0. But the thing is, it's not really important that it's not moving. The important thing is there's no change. Speed 1 and speed 2 are the same value, so there's no change in speed. So if delta Y is negative and delta V squared is 0, what does that tell us about delta P? Right, delta P has to be positive so that these still add up to 0. So if the height is decreasing from 1 to 2, then the pressure has to be increasing. So that means we know that point 2 is higher pressure than point 1. Point 1 is low pressure, comparatively speaking. Point 2 is high pressure. And we can even calculate how much pressure we're gaining. We know this is 0, so you can solve for delta P just by subtracting rho g delta Y. Delta P equals negative rho g delta Y. So we know the density of water, 1,000 kilograms per cubic meter. We know the acceleration of gravity, about 10 meters per second squared. So you can multiply 10 times 1,000 is 10,000 times the change in height. Also, delta Y is a negative value. In this case, -5. And then we've got a negative here, so those negatives cancel out. We just get positive 50,000. And since everything is in kilograms, meters, and seconds, this is going to work out to just pascals. So from location 1 to location 2, there's an increase of pressure by 50,000 pascals, or we would just write that as 50 kilopascals. So from 1 to 2, there's an increase in pressure of 50 kilopascals. Location 2 is 50 kilopascals more pressure than location 1. Any questions on that so far? And if we want to attach some actual values to the pressure, anyone know what atmospheric pressure is? This one is generally assumed to be about 100,000 pascals. 1 pascal is actually a very small amount of pressure. Like if you take, I mean, 1 kilogram per cubic meter, or no, sorry, 1 Newton per cubic meter. My usual standard of reference is if you take like the usual size of Gatorade bottle, about this big, fill that up with water, that's about 1 kilogram of water, which means about 10 newtons of weight, because you multiply mass times gravity. Take that bottle of water, pour it out over 1 cubic meter of space, so like maybe a tabletop or something. The pressure of that water pushing down on that tabletop, that's about 10 newtons of weight spread out over 1 cubic meter. So a bottle of water poured out over a tabletop is about 10 newtons per cubic meter. That's about 10 pascals. So 10 pascals is about the pressure of just a bottle of water poured out over a tabletop. The pressure of the atmosphere is 100,000 pascals. So 1 pascal is a tremendously small amount of pressure. It's 1/100,000th of just the pressure of the air around us all the time. So that's atmospheric pressure. 100, well, it's more like 101,300 pascals. Or if you just want a rough estimate, about 101 kilopascals. In fact, for quick estimate purposes, we often just round this off to about 100 kilopascals. It's actually 101.3 kilopascals, but 100 kilopascals is close enough for quick estimates. And we often just call that 1 ATM. But ATM is not really a useful unit of measurement in its own right. It's just 1 ATM just means the pressure of the atmosphere. So we often describe pressures as like 3 atmospheres of pressure, or 5 atmospheres of pressure, or half an atmosphere or something. But 1 ATM, 1 atmosphere, means 101.3 kilopascals, 101,300 pascals, or approximately 100 kilopascals. Any questions on that so far? So if we say pressure 1 is 100 kilopascals, let's go ahead and be a little more accurate, 101 kilopascals. What would pressure 2 have to be? Yeah, we're just adding an extra 50 kilopascals. 101 plus an extra 50 would be 151 kilopascals. In other words, about 1.5 atmospheres. So at location 1, your pressure is 1 atmosphere because you're just exposed to all the air of the atmosphere. If you go down 5 meters underwater, your new pressure is 1.5 atmospheres, 151 kilopascals. So by losing height, you've gained pressure. And this is why your ears pop if you swim down to the bottom of a swimming pool. You're exposed to more pressure because you're under all this weight of the water. And so the extra pressure pushing in on your ears, I mean, really pushing in all over your body, but you feel it most strongly in your sensitive inner ear, which is very responsive to minute changes in pressure. So go down under some water, you feel like the water is pushing in on your ears because there's more pressure on the outside than there is on the inside of your head. You can balance that somewhat by holding your nose and blowing, because that increases the pressure inside your head so that it matches the pressure outside your head. Because you're not really noticing a pressure. Your inner ear doesn't notice pressure. Your inner ear notices differences in pressure. And in fact, this is true for any measurement of pressure. You can't really measure pressure directly. You can measure differences in pressure. When you attach a pressure gauge to a bicycle tire or a car tire and it tells you what the pressure is, it's not really directly telling you the pressure in the tire. It's telling you the difference between pressure inside the tire versus pressure outside the tire. And this is what we call a pressure gauge. So if you have a tire and you've got air inside, and you've got air outside, and let's say those are at P1 and P2. P1, of course, is just going to be atmospheric pressure. And P2 is going to be some higher pressure. If you attach a pressure gauge to this, the pressure gauge is just a cylinder. I mean, the simplest pressure gauge is just a cylinder tube with another cylinder that pops out of it with markings on it. The smaller cylinder pops out of the larger one because there's a difference in pressure. The difference in pressure pushes that smaller stick out of the cylinder, and the more difference in pressure is, the more it gets pushed out. And then you take a look at the tick marks and read off the pressure difference. So this shows the difference in pressure. Specifically, the inner pressure minus the outer pressure, P2 minus atmospheric pressure. And we call this difference the gauge pressure. This whole thing is called the gauge pressure. Gauge pressure because it's the pressure that's measured by a pressure gauge. So if you see the term gauge pressure, that means the difference between the pressure at the location you're looking at versus atmospheric pressure, 1 atmosphere. For example, at location 2 here, the actual absolute pressure was 1.5 atmospheres, or 151 kilopascals. What would the gauge pressure at location 2 be? If we know the actual pressure, we usually call the absolute pressure. So the absolute pressure means what's the actual pressure at that location. Yeah, the gauge pressure would be 50 kilopascals, because gauge pressure means the difference between the actual absolute pressure versus the atmospheric pressure. This location it has an absolute pressure of 151 kilopascals, but its gauge pressure is just how much above and beyond 1 atmosphere is it. And so that would be 50 kilopascals. The gauge pressure would be P2 equals 50 kilopascals, or half an atmosphere. And in a lot of ways, the gauge pressure versus absolute pressure is a lot like the difference between Celsius and Kelvin. Celsius and Kelvin the units of measurement are the same. Like if you increase the temperature by 5 degrees Celsius, or if you increase the temperature by 5 Kelvin, that's the same change in temperature. If you're talking about a change, it doesn't matter which unit you're using, Celsius or Kelvin. But Celsius, what does 0 Celsius mean? If we say the temperature is 0 Celsius, what does that mean? That's the freezing point of water, yeah. It's a useful reference point because water is a common material to use. But there's nothing intrinsically special about 0 on the Celsius scale. It's possible to get the temperature down to 0 Celsius. It's possible to go beyond 0 and have a negative temperature. 0 Celsius doesn't mean there's none of something. It just is a useful reference point. Likewise, if your temperature is 5 degrees Celsius, that doesn't mean there's 5 of something. It just means you're 5 tick marks above the reference point. But what about 0 Kelvin? What does 0 Kelvin mean? If we say the temperature is 0 Kelvin, what are we saying? It's absolute zero. It means there is actually 0 of something, specifically 0 energy per mode. Absolute zero, 0 Kelvin, means that you have removed all of the thermal energy from the substance. It cannot get any colder than that. So that means absolute zero, 0 Kelvin really does mean 0 of something. You can't go below that. You can't have a negative Kelvin temperature. And if your temperature is, let's say, 5 Kelvin, that really does mean 5 of something. 5 Kelvins means 5 above actual 0. The difference between gauge pressure versus absolute pressure is very similar to that. If we say the absolute pressure is 151 kilopascals, that means 151 of something. If we say the absolute pressure is 0, that really does mean no pressure. And you can't go below that. Your absolute pressure cannot be negative because 0 pascals of absolute pressure really does mean no pressure at all. For gauge pressure though, if we say gauge pressure is 50 kilopascals, that doesn't mean 50 of something. It means 50 above what? 50 kilopascals of gauge pressure means 50 kilopascals above and beyond what? Well, what would 0, if we set the gauge pressure as 0, what does it mean if the gauge pressure is 0? No change in pressure from where, or from what? Yeah, from the atmosphere. If the gauge pressure is 0, the only way this could be 0 is if P2 is atmospheric pressure. So if your bike tire has the same pressure as the atmosphere, if it's completely flat, then the gauge pressure will be measured as 0. But 0 as the gauge pressure doesn't mean there is no pressure. It just means you're at the same pressure as the reference point, the atmosphere. So just like 0 degrees Celsius doesn't mean you have no temperature. It just means instead your temperature is the same as a reference point, freezing point of water. Likewise, 0 gauge pressure doesn't mean you have no pressure. 0 gauge pressure means your pressure is the same as the reference point. In this case, the pressure of the atmosphere. As opposed to 0 as the absolute pressure would mean you actually have no pressure at all, like the vacuum of empty space. Also, what would it mean to have a negative value for gauge pressure? If the gauge pressure is negative, what sort of thing would have to happen in order for this calculation to return a negative result? Yeah, P2 would just have to be less than atmospheric pressure. So it is entirely possible for gauge pressure to be negative. If the gauge pressure is negative 5 pascals, that just means the pressure you're looking at is 5 pascals lower than atmospheric pressure. And you can totally do that. If you just take a sealed box and suck some of the air out of it, that box now has a pressure that's less than atmospheric pressure. So that would be an absolute pressure of maybe 95 kilopascals, but would be a gauge pressure of negative 5 kilopascals. So a negative value for gauge pressure is possible. That just means less than atmospheric pressure. But you can't have a negative value for absolute pressure because 0 absolute pressure actually means no pressure. And you can't have less than no pressure. So these do mean, they're different ways of measuring the same concept, different ways of describing how much pressure there is. You don't want to get them mixed up. But keep in mind that if you're talking about gauge pressure, the atmosphere counts as 0 because that's the reference point. If you're using absolute pressure, the atmosphere counts as 101 kilopascals. But if you're looking at a difference, which is usually what we care about, delta pressure, if you're looking at a difference, it doesn't matter which one you're using as long as you're consistent about it. Just like for delta temperature, you could use Celsius or Kelvin as long as you're consistent about it. For delta pressure, you could be using absolute pressure or gauge pressure as long as you're consistent about it. Because you convert between gauge pressure and absolute pressure by adding or subtracting 1 atmosphere. If you're subtracting P2 minus P1 anyway, if you just add P atmosphere to both of them, the P atmospheres are going to cancel out anyway. So as long as you're consistent about it, it doesn't matter if you're using gauge pressure or absolute pressure. And you can always convert just by adding or subtracting 1 atmosphere. Any questions on that? All right, looks like we are about out of time for today, but we can look into some more examples and more details on this next time. As always, feel free to email me if you have any questions, and I will see you later.